This is the inverting summing amplifier. It's a very interesting circuit, and we're just illustrating it here with the 3 inputs, although we could have as many inputs as we like. And we're going to try and figure out what the relationship is between the inputs and the outputs. The first thing we notice is that the non-inverting input goes to ground. Now recall that one of the basic characteristics of an op-amp is that it tries to operate in such a way that these two voltages, the inverting and non-inverting inputs, are the same. So that means that the voltage here at the inverting input is in fact equal to 0, and we call this a virtual ground. Virtual ground because it's obviously not connected to ground, but it looks like ground. The voltage is 0, and no current goes into it. Now, on the real ground, of course, the real ground will be in fact 0, and you can put as much current into it as you want, and it will not change from 0 volts. In this case, of course, we're putting no current in. So as we begin to look at the circuit, and we notice the voltage goes in here, and this other end of the resistor side to ground, then we realize we have a current flowing in here, and we'll just call it I1, and we have a current flowing here, I2, and a current flowing in here, I3, and we wonder where is that current going? Well, it's not going into the virtual ground because this is high impedance. In fact, the only place it's got to go is right here. It's through R4. So this becomes I4. The other interesting thing to note is if we look at the direction of the current, polarity at this end of the resistor will be positive, positive, positive. Likewise here, positive, and notice that that means that this end over here is negative. That means that the output here, in fact, is negative with respect to the input. And we would expect that because this is an inverting input. So therefore, the output is going to be the opposite polarity of whatever goes in. So now let's see how we can determine what the relationship is between input and output. The first thing we notice is that I1 is equal to V1 divided by R1, that's Ohm's law. And I2 is equal to V2 divided by R2. And I3 is equal to V3 divided by R3. And then, of course, we just finished stating that since these currents do not go into the input of the op-amp at high impedance, they must go in this direction through R4. And so therefore, I4 is equal to I1 plus I2 plus I3. But the other thing we notice is that this end of R4 is attached to the virtual ground, and this end is attached to V out. And because the current is flowing in that direction, this is, in fact, negative. So now we can write another equation which says I4 is equal to minus V out divided by R4. So now what we're going to do is we're going to equate this expression and this expression. And when we write this one, we're going to substitute each one of these individual values here into it. So now we can write that minus VO over R4, that's I4, is equal to I1, which is right here, V1 divided by R1, plus I2, which is right here, V2 divided by R2, plus I3, which is V3 divided by R3. And therefore, of course, we can cross multiply, and we can say that V out is equal to, we just stick the minus in front of all of these things, V1 times R4 over R1 plus V2 times R4 over R2 plus V3 times R4 over R3. So now this looks like a fairly complicated expression, but we can simplify it enormously. We can use it in this general form as it is now, or we can do something very, very interesting with it. What we're going to do is we're just simply say let all of these R's at the bottom here, R1, R2, R3, all equal the same value, let's say as an example. So we'll just simply say let R1 equal R2 equal R3 equal, we'll call it R in. And we're going to let R4 equal R, and we'll call it F. We'll call this F for feedback. So now notice what happens. All of these resistors at the bottom here are the same, Rn, and this is just Rf. So then we could say VO is equal to minus V1 plus V2 plus V3 times Rf, the feedback, divided by R in. And notice what we have. We have an output voltage was equal to the sum of the individual voltages times some kind of a gain here. And of course, we could make the gain equal to 1 if we wanted to. And so that's why this is called an inverting summer, because it sums or adds the inputs and then it inverts the polarity. This type of circuit has a number of applications. Perhaps the one that would come ready to mind would be in the audio industry, where these might be inputs from different musical instruments. And so we could combine them to make a one track. Now, in this particular example, you might wonder, how can we control the volume of each individual input? Well, there's several ways we could do it. We could attach each one of these to their own op-amp and control the gain of that op-amp. Or what we could do is we could modify the input of this circuit slightly. And so let's see how we might possibly do that to make this an audio application. So we'll make an audio mixer. And the way we would do that is we have voltage in, let's call it 1, and it would go to some sort of potentiometer. And we might make it a 1K potentiometer, let's say. So imagine if this is 1 volt, then the current flowing here is like 1 milliamp. Now then, we take this and make this any value we'd like pretty well, but let's make it substantially larger than 1K. Let's make it, let's say, 50K. And this goes into our summing node. And then we would take the next one. Okay, resistor, this would be V in 2. And this would also go into the amplifier. Here we are. And of course we have our feedback resistor over here. And just to keep things very simple, we'll just make this value 50K. And notice what happens. The output from here is going to be some fraction of V in 1 plus some fraction of V in 2. So we could easily put 2 or 3 or 4 or 5 or 6 or 10 different musical instruments and microphones into each one of the inputs, and by adjusting this potentiometer, come up with a different value, with a combined value here. And we could, of course, also control the overall gain by adjusting this pot, but rather than doing that, it would be much simpler if we would simply put this into yet another amplifier that would allow us to control the gain separately. So we would do something like this. And then we might control this, use this as our master gain control. And because this is an inverting amplifier, followed by an inverting amplifier, then there's no phase change. This, in fact, is a positive output, and these are positive inputs. So there's a very simple example of how we might use an operational amplifier to make a very simple, effective circuit. If one was to try to do this using transistors, of course, we'd have all kinds of biasing configurations and nonlinearities to worry about and all that kind of stuff. But with op amps, it becomes really, really, really easy.